Da det Odd og Øystein, eller Odd her da, så...
Ja, jeg vet ikke om Øystein med oss eller ikke.
Jo, det tror jeg kanskje det Ja, skal vi prøve å finne ut det, eller?
Trenger ikke.
Nei, vi sier hei til Øystein.
Yeah, so I prepared these slides in English. I think I'll stick with that, otherwise I'm going to get confused somewhere in the middle. My name is Odd Andersen. I work as a senior researcher at Sintef Digital, the Department of Applied Mathematics and Cybernetics, and in a group that is called Computational Geoscience. And we work on the simulation or building simulation technology mainly for subsurface applications. So the presentation today is prepared together with my colleague Øystein Klemetsdal, and we will present this the work we do in an innovation project with Ruden Energy, Ruden AS, that presented just before lunch, where we are working on developing a digital platform to optimize design and management of geothermal systems for production and for seasonal storage of heat. So this is a software that we are building for Ruden, but we are building it on top of our own open source software that we have at Sintef in our research group. So the basis for this, the software basis that we build on is our open source MATLAB reservoir simulation toolbox, which has been in the development for about 15 years, I think. And it's mainly what you need in order to build a simulator. So it provides you with all the infrastructure and the solvers and the things that you need, the grading and so on. And it's focused mainly on subsurface applications, but we also use it for other types of simulations. And porous media flow is the main target. This has a large international user base by now. I won't cite all these numbers, but it has established itself in the subsurface community as one of the things you go to for designing your own simulation or simulators. And it's used both in academia and industry. But today I'm going to talk about this digital platform that we're making. We are drawing mainly on two modules from MRST, which is the geothermal simulation module and the nonlinear optimization module. So the geothermal simulation module contains functionality that benefits also from all the work we have been doing over the years on oil and gas type simulations. So we have advanced well modeling, for instance. We have fractures, we have complex industry standard unstructured grids, and we can control wells by groups and so on. The nonlinear optimization module contains functionality that we can use when we work on this platform to, for instance, calibrate model parameters to observations or to optimize operations. I'll get back to that a little later. The digital platform concept is that we have not just the subsurface reservoir, but that this has to work in a system that contains a lot of surface facilities. And in order to really, if you want to optimize operation, you have to consider the system as a whole. So the idea here, or the design, is that we can take these different components and then chain them together in loops that kind of transfer energy between themselves. And you can set these up and then model the whole thing as one big simulation. And then you can adjust the control parameters and you can optimize operations. And also, of course, you have to consider that this is working in a larger environment where you have fluctuating energy prices, you have supply and demand that varies, and so on. So that is also something that has to be taken into account. So I'll show some examples on what we have done with the platform so far. But first, I just want to show a little bit why we insist that it's important to do detailed simulations of the subsurface. So I'll just show a couple of examples where we really see that we need detailed simulation in order to get the correct representation of the subsurface. And I'll try to do this relatively quickly. I'll just show a conceptual case where we have an injector in the middle, injecting hot water, and then we have producers on each corner of this grid, very simple grid. And then we can either do it without fractures, we can have 3 horizontal fractures or 15. And in each case, we just tune the permeability of the rock matrix so that you have the same kind of circulation. It's just that the circulation pattern is different when you have the fractures in place. So if you look at the heat profile, when you just have no fractures, then you see that you get a nice utilization of your heat store. The heat is kind of evenly spread out. If you have a high permeability corresponding to a case where you would have fractures with a quite high aperture, then you would have a more like wine glass shape, but it still kind of expands uniformly outwards.
It's homogeneous.
Homogeneous, but you're trying to emulate the same upscale permeability as if you had fractures. The picture, if you have explicit modeling of fractures, is very different, as you can see here, because then you have only transport in the fractures, and then you have diffusion into the rock, and then you have a much lower total storage capacity for the same amount of water injected. If you have a certain number of fractures, like here is an example with 15 fractures, then you get something that is more close to the homogeneous situation. So in that case, you could perhaps imagine simplifying your problem. But here also there's another thing that requires detailed modeling that pops up on this simulation, because we see here that there's a lot of injection of heat at the bottom that is actually not physical. This is because we're using a quite simple well model where we don't model the behavior internal of the well, so that you don't have the exact density variation in the well. You don't have the exact temperature variation, which means that hot water is reaching down to the bottom where a more detailed simulation would show that it doesn't go. So when we introduce a multi-segment pad well, where we really model what's going on inside the wellbore, we get a more physically correct result. So we eliminate this, and also even if the other one has a certain change on the bottom. I'll just quickly mention an example where we use this fracture modeling and advanced well modeling to investigate a real case. This is again in Tromsø, the Kvitebjørn site that Eivind presented before lunch. So we have done some studies that have still on the quite conceptual level, because we don't have all the data from the actual site yet. We are still waiting for that. But we have tested the concept with various number of induced or produced fractures, and then compared the performance of the system and so on, and come with some preliminary recommendations from this study. This was just to show that this is actually, these details are important. It's just not an academic exercise. Just some examples now from where we have applied a digital platform. Of course, this is still something that is under development. We still have this year or parts of this year left in the project. And this example I'm showing here is this is more like an academic exercise, I think, but I didn't have time to prepare a more advanced case. So here we have a setup of the system where we have a geothermal reservoir that is connected in a loop with a heat pump and a heater. And then on the other side, we have an external heat source that provides energy. And then you can run a charge phase, then you will, of course, pump heat from the heat source, and then into the loop, the heater will add supply additional energy in order to have a constant injection temperature. And then in this charge phase, you kind of run the system in reverse, and you deliver heat to some consumer. So we just imagine a scenario where you want to charge the system or you have the option to charge the system for 15 days. So this is just very short term. And then there's a discharge period where you anticipate higher prices on the energy. It could be like a road heating scenario after a snowfall or something, but again, this is kind of a simple simple exercise. And then the energy price for the supplied heat will be quite low, and then you will have a higher price when you have to withdraw the energy quickly for the last 4 days. So you have the choice of not storing energy. You have the choice of storing energy with a kind of reasonable setting, and then you can try to optimize the system by adjusting temperatures and rates. And in this case, with the optimization algorithm, which is also, by the way, it's automatic, so it's not like you have to tune these things yourself. We see that the cumulative cost is on the right. So then you see the time. So 15 days of no charging, and then supply everything by electric heating. That's the black curve. And then you can see that there's no cost first, and then it rises quickly. And then you have the blue curve, which is the unoptimized system, where you inject heat, but you don't do it in an optimal way. And then the red and yellow curves are where you have run the optimization procedure to tune the rates and temperatures. Either you can just have a constant rate and constant temperature for the charge phase and for the extraction phase, or you can even vary during each of these phases, which is the difference between the yellow and the red. So yeah, in this simple example, you can have cost reductions of up to around 50%. Another application of the platform is in calibrating to measure data. I'll use a different example that was presented by Ruden before. This is it's a representation of one of the geological reservoirs that they are working on at the Vestkvartalet in Asker. So here we have actually measured data for a year of production temperatures, and we are trying to reproduce that using our simulator. We have here a relatively conceptually simple representation of the shallow reservoir that they have there. It's in reality it's like 100 wells or so. We are using each well group as a separate well in order to simplify the problem. And then we look at the produced temperatures that we simulate and compare them with actual observed ones. If we run this simulation with kind of best guess parameters for pore volumes, rock probability, heat transmissibility, and heat capacity, we here produce these temperatures that follow the blue curve. And these are the different well groups that you see here. For each well group has a specific measured temperature. So we see the blue doesn't really match the observations, which are the circles. But when we run the automatic parameter estimation to change these parameters, we get, and then we have trained it on the red part, or the circles that are on the red curve. And then when we simulate, we produce the red curve. So we see there's a very good match. But even in the yellow part, where we did not calibrate, and these data did not go into the calibration, but our simulator then predicts temperatures that still match quite well with what is observed. Yeah, I'll round up there. So to conclude, we're working on this integrated framework for modeling and optimization geothermal heat storage systems, where we model the system as a set of interconnected loops that includes not only the reservoir, but also the surface facilities. And I have highlighted some of the important simulation modeling aspects, like the fractures and the wells, that needs to be carefully considered. So with that, I thank you for your attention, and acknowledgement to Ruden, Vested Energy, and to Bjørn for allowing publication of this work, and also for providing the data and good dialogue throughout the project. Thank you.
Julia.
Thank you. I'm wondering, what is the optimization method that you're using?
To get technical, we call it's non-linear adjoint-based continuous optimization. So it's a mathematical technique where you describe your objective function as a function of your parameters. And then you can see how your objective varies when you tune the parameters by kind of inverting your physical simulation system. So that you see basically the derivatives or the gradients of your control variables with respect to or you see the gradient of your objective function with respect to your control variables by passing them in reverse through the simulation system.
Nils, what kind of learning? This is a question to both of you, but we now saw two talks that are very kind of far from each other in some sense. But I mean, what kind of learning points can you take from this when it comes to optimization and better use? Are you? This is kind of a critical question to us as scientists. I mean, how can we assist the deployment of these technologies in the best possible way? Can you comment? You can say whatever you want.
Because following and reading all the projects we've done will, of course, give us a lot of learning. But we also do that in our own projects to measure and learn, of course. But to have new and better systems to do it, also provide good lessons for us. So
I think one point to make is that the simulation that we have worked on with this project is really mainly focused on open fractured systems. Although it could also be applied in other settings, but I think the open fractured systems are among the most challenging to really understand, where you really need to have a good understanding through numerical simulation.
Yeah.
It will be the same in a heat storage, but it's important to have a system so we can calculate at first, and you have to develop and measure during the system over years. So you can make sure that your data is correct.
Yes,
it's very necessary to, when you build new systems, that you have good enough data first.
Yes, you really need to calibrate your model so that you actually can use it for prediction and not just for experimentation.
Yeah.
Just a question for, if there's time, displacement for the non-fractured and the non-fractured. Is that correct? So it's for understanding the difference there. And are there differences in timescales between these figures?
I mean, you can choose whether or not to use fractures depending on the nature of your model. Like if you have a lot of fractures that are very closely spaced, you can also try to model it in an upscaled way where you don't explicitly represent each fracture. But of course, the explicit representation of fractures give you a better precision, but it also is more computationally costly. So it's a trade-off for what you want to do.
Okay.
But you can still use it.
So, but are these, so is it an analytic porous flow model and a flow model for the gaps that are different, or is it all 3D? I'm just wondering about the.
Oh, well, it's a fracture modeling technique. It's called discrete. It's basically one way of what's called discrete fracture model. So you have explicit fractures in your grid that is treated like cells in many ways, but there are some special adaptations for it.
So there's a different, okay, very good, thank you.
Zoom quit expect. So I got a message here from Zoom. Kirsti, what do you see in
Det ser presentasjon, så det ser bra ut nå.
Ja, men det flott. Da bare kjører vi på. Da